This is the back page of the related rates worksheet, number 3. Back page starting with number 3 here. This is another older College Board FRQ. All right, so as shown in the figure above, the water is draining from a conical tank with a height of 12 feet, diameter of 8 feet, into a cylindrical tank that has a base with an area of 400 square feet, and the depth of the water is changing at a rate of h minus 12. All right, so water is leaving the conical tank and going into the cylindrical tank. But the first part, we're going to deal with the cone. So part A, write an expression for the volume of water in the conical tank as a function of h. So we start off with our volume equation. Our volume is pi over 3 r squared h, but we want to be able to write this as a function of h. So we want to basically replace r in terms of h. So if to do that, when we deal with cones, we can always relate radius and height using similar triangles. So if we cut this in half and just look at a two-dimensional figure, we can create similar triangles, one representing the dimension of the cone, and then the other representing the water level in the cone, or in the tank. All right, so we know the radius of the tank is going to be 4 feet since the diameter is 8. We know the height of the cone tank is going to be 12 feet. And the water level at any moment in time is going to be given by radius r and then variable h, since these values, depending on where the water level is, can be changing over time. So we're going to set up a proportion to relate radius and height. So we can say the radius of the small triangle is to the radius of the large triangle, r over 4, as the height of the small triangle is to the height of the large triangle, so h over 12. If we do cross product, we get 12r equals 4h. Solve for r is equal to 4 over 12h, or h over 3. So now we have something that we can do to replace r with. We know r can be replaced with h over 3, and that will get us closer to creating an equation in terms of h. So r gets replaced with h over 3. So h over 3 squared is a replacement for r squared. And if we clean this up a bit, h over 3 squared is h squared over 9. And if we combine this, we get pi over 27, and h squared times h will be h cubed. So here we have our volume equation in terms of h. Part B, at what rate is the volume of the water changing when h is equal to 3? Okay, when the height is equal to 3. We're trying to find the rate of change of the volume of water, so we're looking for dV dt. So let's come back to where we ended up with. Part A, we left off at a volume equation in terms of h, so we can use this to find dV dt. So V becomes dV dt. Pi over 27's coefficient, it just stays. We find the derivative for our h cubed, which becomes 3h squared dh dt. Simplify, we get 3 over 27 reduced to be pi over 9 h squared dh dt. All right, so at the moment when h is equal to 3, so we know h can be replaced with 3. And we know dh dt can be replaced with h minus 12, because we're told that the depth, or h, is changing at a rate of h minus 12. So we're told in description what dh dt is. So the rate of change of height is going to be h minus 12. So we know dh dt is h minus 12. So we plug that in for the dh dt portion of our equation. H again gets replaced with 3. So we get pi over 9, 3 squared times h minus 12. And we know the h at this moment in time is 3. So 3 gets replaced for h. So 3 minus 12 is negative 9. 3 squared is 9. The 9's cancel out. We're left with negative 9 pi cubic feet per minute. And the negative should make sense because we know that the volume of this cone is going to be decreasing over time since water is draining out of the cone. So it makes sense that the rate of change of volume will be a negative value. Okay, part C. Let y be the depth in feet of the water. Of the cylindrical tank. At what rate is y changing when h is equal to 3? So we're now dealing with a different shape. We're no longer dealing with the cone. We're dealing with the cylinder. So cylinder, we'll use y to represent the height of the water level. And then I'm going to use a to represent the radius of the cylinder. I don't want to use r since r has been used for the cone. So we'll just use a. Let a represent the radius of the cylinder. All right, so part C. Let y be the depth of the water and depth of the water in the cylindrical tank. At what rate is y changing? So we're trying to find the rate of change of the depth of water. So let's first start off with what is the equation for our cylinder. So cylinder is going to be v is equal to pi r squared h. But instead of using r and h, we'll use a to represent the radius of the cylinder, and then y to represent the height of the cylinder. So, or the water level's height. Okay. So now something that we know is that as water, we know that water is draining out of the cone into the cylindrical tank. So we expect the volume to be increasing over time, and then we also expect the water level to be rising. So we know y is going to be increasing. But what about the radius, the a value of the cylinder? No matter what's happening to the water level, the radius of the cylinder is going to remain constant, unlike the radius of the cone. Okay? We know this is changing over time, but we know that if we can figure out what the radius is, then that will remain a constant because that's not going to be changing over time. So if we can find out what a is, then we can plug that value in. All right, we're told that the tank has a base with an area of 400 pi square feet. So we know the area of this circle base is going to be 400 pi. So from there, we should be able to figure out what the radius of the cylinder is. So let's do that. So we know the area of the base is 400 pi. We know that the base is a circular shape, so a is equal to 4 pi r squared. So replace a with 400 pi, and then we can solve for r, divide both sides by pi. We get 400. Take the square root, we get square root of 400, which is 20. So we know the radius of the cylinder is going to remain at a constant value of 20 feet. And then we're going to represent a as the radius. So we know a is 20 feet. Let's go ahead and plug that into the equation because that a value is not going to be changing over time. So we can now simplify our equation to be just 220 squared pi, which is 400 pi times y. All right, so now we're ready for the derivative because we want to find dy dt, right? So v becomes dv dt. 400 pi is a coefficient that stays. Y becomes dy dt. So now we can figure out what dy dt is. We know the rate of change of the volume is going to be, it's draining out of the cone by negative 9 pi cubic feet, but for the dv dt, for the rate of change for the cylinder, it's going to be a positive 9 pi cubic feet per minute, since the volume of the cylinder is increasing, whereas the volume of the cone is decreasing. So that's why there's a change from a negative dv dt to a positive dv dt. We're talking about rate of change for volume for different containers. We're talking about, in this case, a positive rate of change of volume since the water level is going to be increasing in our cylinder. So dv dt gets replaced with 9 pi, and then our last step is simply solving for the dy dt, which represents the rate of change of the height of the water level or the depth of the water level. So dv dt is 9 pi. We can divide both sides by 400 pi. The pi's cancel out. 9 over 400 is equal to dy dt. So there we have it. The rate of change of the height of the water tank is going to be 9 over 400 feet per minute.